All right, now that we have our first smart contract in Remix, I think it's time to actually talk about how smart contracts are working a little bit more under the hood. So you have the theory side as well. Now, in general, what is a smart contract? The term itself was coined by a computer scientist named Nick Szabo already in 1994, so it's not particularly new what smart contracts are. They are a piece of code that is running on the blockchain. And the blockchain itself is like a state machine, so it needs a transaction to change from one state to the other, and it can do some logic operations. So that is basically how that thing works. And the state change happens through mining, and the mining is going to take the transactions that are in a transaction pool and then changing the state on the blockchain. Now, the Ethereum blockchain is a Turing-complete blockchain. So that means in theory, it can solve any computational problem. And it's just a theory because it's very limited by the computational power that it has. You will see it later. It's calculated in the gas amount. So if you need a certain amount of gas, which is getting too much, you cannot in practice solve any computational problem, but in theory you can. So in theory you have all the functions and all the logic there to solve anything that needs to be solved. Now there are a couple of programming languages for Ethereum virtual machines, and the most popular one is Solidity, but there's also Viper, which came from Vitalik, wanting a new language that is more secure and a little bit also more for academic purposes. Then there was LLL, which I think looks a little bit like Python, but there's no development for these languages anymore. And then there was Bamboo, and there were a lot of other languages that basically compile the source code into EVM bytecode, and that is what is run on the blockchain. So the EVM bytecode is actually the kind of code that the Ethereum blockchain nodes are executing. And then there's high-level languages, very much like C, C++, what do we have? Go, and so on. So those languages, you can write them in a specific syntax, and you have specific language features, and then they compile down to the actual bytecode or assembly code for the EVM. And this stays constant, and the language features change. Actually, the EVM also doesn't stay constant because there are hard forks, but more on that later. So how about Solidity? I mean, that's by far the most popular language, and this course is also building upon it. We are doing a lot in Solidity, and we are trying to touch on every kind of topic that Solidity has to offer in the projects that we are doing. It is very often compared to JavaScript, and actually it's compared to ECMAScript. And it's like every high language code is then compiled to bytecode, and that is very important to understand. And in the Ethereum network, every node then executes the same code. So you're going to write your Solidity smart contracts in Solidity. It's going to be compiled to EVM bytecode. Then you send the transaction with that bytecode to the blockchain, and then every node in the network is going to execute the same code because every node has a copy of the whole chain. It's very important to understand that. It is not like you're going to send your code to the AWS data center and then there sits a machine that is going to execute the code. It is you send the code to the network, and then the network itself takes care of distributing your transactions across all the nodes that are running in the network, and then those are executing the same code again. Now, as I said before, there are other languages. It was Serpent that is similar to Python. LLL is like Lisp. There was Mutant, and now there's Viper, and in between they also had Bamboo. But I still recommend staying in Solidity because it's really by far the most famous language that is out there for smart contract development. Now, how does a Solidity smart contract actually look like? And it's very tiny here, but I want to touch on a couple of features that the language has that are probably very familiar to some of you who are coming from a language like Java or like C# or like C++. So there is a class-like structure, and those classes are the keyword for the classes are contract. And they contain functions, and the functions can contain control structures like if else. There's loops, for and while loops. There's different data types. It's a statically typed language, so you have to give it for every variable that you define. You have to tell it which kind of data type is that. There is unsigned integers, booleans, arrays, structs. There's mappings, which a little bit look like hash maps. There is a special data type called address that is, I think, not available in any other language that I've ever seen. And be careful, there are no floats. So if you want to have some sort of decimal points, you have to make a large enough integer to take care of the decimal places. And more on that also later when we do our first coin. There's inheritance, so you can have contracts extending other contracts. There is special structures like modifiers that, a little bit like go-to statements in BASIC. And then there is also import, so you can fine-grainedly structure your smart contract files and then just import whatever you need. You will also see that later on. Now, as Solidity layout more at the beginning, what you saw now is that one, what we did in the previous lectures with an SPDX license identifier. That one identifies the license of that file. It doesn't identify the license of the project that is running under. So make no mistake, it's not that because the NFT ERC 721 token file is licensed as MIT that the NFT is licensed as MIT. It's about the source code. So this one depicts the license of the source code, as far as I know. Then there is a pragma line. The pragma line is a pre-compiler line that tells the pre-compiler to select the right Solidity compiler for that file, or at least it tells it like this file is written for this compiler version. And that is in a semware style semantic versioning. So in this case, it is clearly 0814, so it's locked into a specific version. And if there was a caret in the front, then it would mean 0814 or larger, but not more than 09, excluding 09. Or you can also use the greater sign, smaller sign, greater equal sign, and so on. So you can use those to tell the compiler or the environment that you're in, the pre-compiler, what kind of compiler version is that file written for. And the reason is that you want to lock in specific compiler version, because sometimes the compilers change and they have a different meaning for the same language features. Now let me give you an example. Unsigned integers and integers in previous versions were rolling over, and I will show you this later. So if you hit 0 and then you decrement an unsigned integer, you suddenly hit max int. And this was changed in, I think, Solidity 086 or 3 or something. So be careful that you lock in a specific compiler version that you're currently working on, and then make sure if you're upgrading to a new compiler version that all of your files are still compatible. This is where unit tests come in, which we're also writing. Now, then comes a contract. This is what I told you before with the classes. The contract is depicted with a contract keyword, and then comes in capword style. Well, you don't have to, but the official naming convention of Solidity, which you can also find in the Solidity docs, is here's a capword style, meaning the first letter is capitalized and then every other word is also capitalized. So the M is capitalized, and then contract, the Z is capitalized. And then if there would be other words, then you would also capitalize them, at least the first letter. Then there is curly brackets, and then inside the curly brackets this one is a storage variable, which we are talking about later on. It's basically the variable that stays across several transactions, so you can store some value in there. There's going to be events and modifiers and functions and constructors, and all of the other things that we want to do with Solidity are in there. Now for the deployment, we sent off a transaction, and when you had a look, when you opened the transaction field in Remix, then you probably saw that there was a data field or a value field that was populated. It's called input field in Remix, but it's actually for the transaction, it's a data field. And this data field has the compiled bytecode. And that one, if it's not sent to any specific address, if the to field is empty, then the EVM will know, wait, this is bytecode, I have to deploy it to the blockchain, and then it will create a new address, which is a deterministic operation, will create a new address for the smart contract, and then it will deploy the smart contract bytecode that is sent in the data field in the blocks, in the blockchain. And that's how it is. And this is what we are going to do now in a couple of next lectures over and over again, so you understand exactly how this works. But this is the basic. So this is the very basic. If you understand that, then you understand already 80% of how smart contracts are deployed, how the interaction works, and so on. Now, the key takeaways are the smart contracts are running on the blockchain and they are deployed as EVM bytecode. The blockchain itself, or the EVM, is a Turing complete system. The structure for a smart contract, if you had any prior coding experience, should look fairly familiar. Even if you come from only JavaScript or only PHP, it should still look very familiar. So there shouldn't be much of a new thing other than the addresses and the special edge cases like no floating points. Deployment is done with transactions, and this is going to change the state of what is basically a state machine, the blockchain. All right, I will see you in the next lecture.